In this lab, we will be finding the unique mass of a black hole using computational modeling and creating a trajectory that allows our ship to leave the planet, get close to the black hole, and then leave the system entirely. The key concepts we will be using are Newton's second law of motion, which states that the net force acting on an object is equal to the parallel force and the perpendicular force. And we'll also be using the gravitational force equation, which states that the force of gravity is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by r squared. In part 1, I used my Georgia Tech email address to create a unique seed for our black hole. We have a few known constants, including the gravitational constant, the mass of the star, which was given to us in the instructions, and the interval, the time interval, which is the number of seconds in 24 hours, which is 8. To find the initial momentum, we use the initial and final momentum, we use momentum is equal to mass times velocity, and then found the delta V and delta P by doing final minus initial. Our dp dt is equal to the delta P over delta T, the change in momentum, and we set our net force equal to that because of Newton's second law. We then found the parallel component of our dp dt, parallel net force. We know that the total dp dt is equal to the parallel and perpendicular components. So all we had to do was subtract the parallel component from the total dp dt to find our perpendicular component, and then set our fnet perpendicular to it. If we run the program that we discussed just a second ago, we can see that the star moves in an orbit and the force net and perpendicular components point towards the black hole. We then take the data that we got, which produced over 400 data points, to find our mass of the black hole. You took the average of all the data points and got approximately 1.51 times e to the 34th power. In part 2, we used the mass of the black hole that we found from part 1 and the same constants, along with the mass of a planet that was given to us and the mass of a ship. What we want to do is create a trajectory that allows the ship to leave the planet, get as close as possible to the black hole, and then leave the system entirely without crashing into anything. We found our values through trial and error using computational modeling. Our speed in the x direction was negative 3.8 times 10 to the 7th meters per second, and our y direction was 2.59 times 10 to the 6th meters per second. We know that the force of gravity is equal to, again using the force of gravity equation, we solve for the force of gravity on each object, acting on each object. Our first section focuses on finding the force of gravity on the planet by the black hole and on the planet by the spaceship. Our second section focuses on finding the force of the ship by the black hole and by the planet on the ship. We use the Newton's second law and the position update formula to make the planet and spaceship move. So the planet velocity is equal to the previous velocity plus the net force divided by the, and for the ship, it is equal to the initial velocity plus the force on the ship divided by the ship's mass times delta T. So what does this mean? How are the net force and rate of change of momentum different? Well, the force net perpendicular component is always pointing towards the black hole, no matter where the star is in its object from part 1. But the change in momentum for the perpendicular and parallel components change based on where the star is. As the star is moving away from the black hole, the momentum starts to point away from it. But as it gets closer to the black hole, the momentum starts to point towards the black hole. What if we wanted to create an orbit and let the spaceship orbit around the black hole instead of trying to leave the system? Well, all we have to do is change the initial velocities, which again we can see the results of our orbit here.